So you can see that numerical methods fever is full on. Okay. But for the next 90 minutes, we'll try to focus on fluid mechanics. Okay, that's okay. So in this module, to remind you, what have we seen so far? We talked about velocity field. We talked about computing acceleration. We talked about how it has three components, local, spatial or convective, and some of those two called total. Okay. So just to put a quick recap, I'm not going to go over all of this again. So velocity is a function of position, or velocity is the function of xyz coordinates, which may be used to define the position in Cartesian coordinates. And each component of velocity may be a function of position. Okay. We talked about what is acceleration. Acceleration total is the total rate of change of velocity, dv over dt, the total rate of change of velocity. Okay. So this is the partial derivative of v with respect to time at a fixed position plus u dv dx u mu dx I cap plus v dv dy j cap plus w dv dc k cap. We won't go too much into vectors. Mostly we will stick to one-dimensional flows in this course. Okay. And for that, this component is the local and this is the spatial. Now, can anyone tell me, when you say local acceleration, what are we referring to? Like, to remind you of a river example, I just stand here at a fixed point and I just monitor the velocity at that point. What is the local acceleration in simple words?
Change in position with the
It's the change in velocity with respect to time at a fixed position, right? It's the change in velocity with time at a fixed position. Thank you. So if it's a steady flow, what does it mean?
zero.
Steady flow means the local acceleration is zero for all time. That is, partial v over partial t is just zero for all time. That will make it a steady flow. If it's momentarily zero, it means it's going through a phase in which it's momentarily not accelerating, but could accelerate or could change in the future. Okay? And then as you go from, let's say, a point, so from point 1 to point 2, there is a change in velocity. Change in velocity due to the spatial gradient of velocity. That is, you are accelerating in the sense that you go from point 1 to 2, like going down a waterfall or going down a rapid. The change in velocity due to the spatial change, that also contributes to acceleration, and that component is what we call the spatial. The book also uses the word convective, so I'll start using that. convective component of the acceleration. So an important component or important quantity that we saw here is velocity gradient du over dx or dv over dy or dw over dz. Okay, in vector form, this is written as gradient operator of, sorry, I'll just speak to scale. Okay, so these are called velocity gradients. Velocity gradient. In one dimension, A total is equal to A local plus A spatial or convective. This is partial U over partial T plus U times du dx. And this is what we'll use in one form or the other for most of our problem solving. For as long as it is one dimensional flow, this is what we need to solve problems like the three examples we did last time. Okay, the velocity was given semi-qualitatively, sometimes numerically, sometimes through a function. In any case, this is what you need to compute those accelerations. Okay. Are you able to recap? Like all this is coming back. This is what we have spoken for the last two lectures. Okay. So one last mention in this before we move on to the next topic. Not only velocity, we can compute the total derivative for any quantity that varies with phase, that is XYZ coordinates or the position and time. We can define total derivative for any quantity, and these quantities could be like density. We use the symbol rho most often. Pressure, lowercase p, temperature, uppercase T, any other quantity label. Can I erase the right side? Yeah. So in one dimension, let's say we think about the total derivative of pressure. This is the local plus the spatial. So our total derivative of density, that is the local plus the spatial. Now take a moment, look at this. When we wrote the spatial derivative for acceleration, we were multiplying by u. When we are writing the total derivative for pressure or density or any other quantity, we always multiply by u. I can go into the math of why we multiply by u, but intuitively, what can you connect from the fact that you are moving, let's say, along the x direction with the velocity u, and the fact that we always multiply by u? What can you connect and tell simply is the reason we multiply? What is this first quantity? This is the local rate of change. And the word local should give you a clue. What does local mean? At a fixed location, right? Local to 1 or local to 2. It is at that point, at any point. Okay. When you think of this quantity, if partial u over partial x is called velocity gradient, what should we call partial p over partial x or partial rho over partial x? What should we call these? Louder, please. Pressure gradient, right? This must be pressure gradient, and this must be density gradient. Here's a way of thinking about this. Whenever you think about rate is a time derivative. It's a change with the time. Whenever you think of gradient, that is a spatial change. It's a derivative with respect to a spatial coordinate. Okay? You can think of it like this. Take Shelby County. Our population will go up and down every year. That is like a local rate of change. You can think of how much Shelby County grows or shrinks over time. That is like a local rate. But at a given time, let's say you compare the density of people in Shelby County and adjacent Fullerton County and maybe a couple of counties in Mississippi and Arkansas, you can see that they are not all even. Like as you go from Shelby in any direction, the population may go up or go down depending on the numbers, right? So that kind of spatial variation is given by a gradient. Anything time is a rate. Okay. So now come back to this. I'm saying the total rate of change of pressure with time is due to time itself and the fact that you are moving along the x direction at a certain speed u, and along that direction the pressure itself changes at a certain gradient, which is partial p over partial x. So the combination of these two is like changing, it's like saying u times partial p over partial x is the rate at which we move along x. That is literally the x component of velocity, right? The rate at which we move along x. That is the x component multiplied by the gradient with which pressure changes along x. You want to write this down because when I was like you learning this topic for the first time, it took me many years to understand this simple idea that you are moving at a certain rate and the quantity itself changes along x direction in a certain pattern. That's called gradient. So you get the product of those two, you get the rate at which the product of these two is the rate at which the quantity changes with time due to motion. This is the keyword, due to motion. This is just due to time only, whereas this is due to motion. I know it's a little messy, but what I would want you to take down is all of this. This is key information that I'll give you time, write it neatly, make sure you remember this and think about this. Let's take a minute for you to finish writing that. Are we done writing? Okay, here's a question for you. Is the unit consistent on all three terms? Or in other words, can you check and tell me if all three terms of this equation have the same unit and what is that unit? We are not doing participation today, but still this would have been a good participation question. What's the unit of the rate of change of pressure with time? That would be Pascal per second, right? Pascal per second. Okay. And the second term is the derivative of pressure with respect to time. Obviously, that will also be Pascal per second. But let's make sure the third term has units of Pascal per second. What is the unit of partial P over partial X? First, Pascal per meter, it's the pressure change over length. And then I have to multiply this by velocity, which has units of meter per second. So that gets me also Pascal per second. It will. I just want to make sure that you saw it. Okay. So all three have the same units, and pressure gradient multiplied by velocity gave Pascal per second. What is the unit of pressure gradient itself? What is the unit of pressure gradient itself? Can you tell me? Sorry, not pressure gradient. Sorry. What is the unit of velocity gradient? Can you tell me? Per second. That is meter per second per divided by meter. So that is per second. Okay. So this velocity gradient always has units of per second. And for reasons we'll see in like when we discuss pipe flow, this is also called shear rate. I'll tell you the reason when we talk about pipe flow, but make a note that velocity gradient is referred in the textbook sometime as the shear rate. I think all of you were here for the last lecture, right? So we did problem 4.24. Do you recall that? Can you look at your notebook and make sure you take a moment to refresh that? And then we'll do today, we'll do problem 4.57. So if you have your text, kindly look at 4.24 and 4.57. So in problem 4.24, t equals 0.0 seconds, 1 second, 2 seconds, 3 seconds, and then for x values of 0.0 meters, 10 meters, and then 20 meters. So in problem 4.24, you velocity component values as a function of position and time were given. Do you recall? You look back, everyone? Yeah. So this was given, and we compute the acceleration, which is the total derivative of velocity with respect to time, or the local plus the spatial. Okay, we did this. Do you remember, recall? We computed the total derivative from the given table of values. In the previous two problems, a formula for u was given or implied, but in this problem, data was given. And data is how you are going to receive information in the real world. Yet nobody is going to often give you a function that's only in exams and courses, but in real world, you might stick a velocity probe and you might read out data that looks like this and you have to process it. Okay. Alright. So what did we, do you recall what we did for the velocity, the local acceleration? For the local acceleration, how did we compute a local, which is partial derivative of u with respect to time at a fixed value of x? What did we do? So let's say we want to compute this for at 10 meters and at 1 second. How will you compute this?
Delta V over delta T.
Louder please.
Delta V over delta T.
This is the delta or change in velocity divided by change in time at x equals 10 meters. So that would be the value of u at 10 meters and 1 second minus the value of u at 10 meters and 0 seconds divided by delta t, which is 1 second minus 0 seconds. And this number, if I look at the values, this is 1.20 meter per second minus 0 meter per second divided by 1 second. That gets me 1.20 meter per second squared. Do you have this in your notebook? Good, right? So the velocity the acceleration at 10 meters and 1 second time happens to be, at least the local component is 1.20. And the total component is u times partial u over partial x at x equals 10 meters. We talked a lot about how to compute the slope. Should we look back or should we look ahead or should we do an average like Isaac mentioned, right? So you can do it either way. These are all reasonable. So you can do. Can you tell me the numbers so I can save some time? What was partial u over partial x that we finally estimated?
Uh, 0.02 seconds.
0.02 per second, not seconds, per second.
Yeah, per second.
So partial u over partial x at 10 meters, x equals 10 meters, was estimated to be 0.02 per second. Everybody has this in their notebook from last lecture. So the spatial acceleration would be 1.20 meter per second multiplied by 0.02 per second, which gets us how much? 0.024 meter per second squared. So the total acceleration would be 1.20 meter per second squared plus 0.024 meter per second squared, getting us 1.224 meter per second squared. Okay, so now in problem 4.57, problem 4.57, it's the same problem, same field. Instead of giving you velocity values, in problem 4.57, pressure as a function of x and t are given. Take a minute, look at the problem. How many of you want me to bring it up on screen and don't have your textbook? Give me 1 second. All right, give me 1 second, almost there. Okay. Can you get the light? Yes, with the first switch. Thank you. Okay, problem 4.57. The following pressures were recorded. Same field, there is same values of x and t. So it's like they at every point they put two sensors, one to record velocity and one to record pressure, and they have provided the data. Okay. Now we want to know, find the local rate of pressure change and the convective rate of change, that is V times partial P over partial X at 2 seconds and 10 meters, at 2 seconds and 10 meters around at this value. Okay, so you have to do this problem using data from both the pressure sensor as well as the velocity sensor. The velocity sensor is a different thing. Okay, that's how most often measurement will be done. You'll be deploying more than one sensor to get you independent pieces of information, and then you combine them in your analysis to calculate something. Okay, so you need to estimate two quantities: the rate of change of pressure with respect to time at 10 meters and 2 seconds. Without having to do anything, can you tell me how you which two numbers or which two pressure values will you use to do the calculation? Partial P over partial T at 2 meters.
0 and x10.
Would it be 131 and 116? Right? I have to take 10 meters. I'm at 2 seconds. I'm looking back 1 second to know how much I've changed in 1 second. Yes? No? Rashid?
Yeah.
Okay. So the answer for partial P over partial T, you can write, I'm not going to write that, is going to be 131 minus 116 divided by 2 seconds minus 1 second, or that will be about 15 kilopascals per second. $15 kilopascals per second. You're with me? Yeah, okay. Now, are we good? Look up, please. Now you want to compute what is the pressure gradient at 10 meters. If you look to your right, from 131, it went to 121. There was a drop off. Look up, please. You can write later. At 131, from 131, it went down to 121. If you look to the right, if you look to the left, from 131, it went up to 141. Or in other words, if you move from left to right, the pressure is steadily dropping at a rate of 10 kilopascal per 10 meters or 1 kilopascal per meter. Okay, so don't get too lost in your number crunching. What you should be able to do is look at a table of data or a graph of data and understand the trend quickly. If you sweep your eye from left to right from 0 meters to 20 meters, there is a drop of 10 meters or sorry 10 kilopascal per every 10 meters. So you don't have to be a genius to write this down. Partial P over partial X is 1 kilopascal per meter. Okay, 1 kilopascal per meter. So you can also look up the previous table, find out what the velocity value here is at 10 meters and 2 seconds, which I can tell you is 1.80 meter per second. So you have P equals 1.80 meter per second. Partial P over partial X is 1 kilopascal per meter. Get me the final answer. Get me the final answer, please. So the total rate of change of pressure is the local plus the spatial. The local is, what did I say was the, local is 15 kilopascal per second. So the local is 131 kilopascal minus 116 kilopascal divided by 2 seconds minus 1 second. That gets me 15 kilopascal per second. 15 kilopascals per second. And the spatial would be U partial P over partial X, 1.80 meter per second multiplied by 1 kilopascal per meter. 1 kilopascal per meter. So that is 1.80 kilopascal per second. 1.80 kilopascal per second.
Where'd you get the 1.8 from?
Yeah, where'd you get the 1.8?
Sorry?
Where'd you get the 1.8 from? Is there like a table that you?
Yeah, this is from problem 4.34. So remember, this pressure data comes from problem 4.57. The velocity data comes from 4.34 or 34 or 27.
4.24. 4.2.
4.24, sorry. 4.24. In the real world, this is a pressure transducer data. This is velocity transducer data. Yes.
With the change in pressure per meter to negative, that's.
It could be negative. It can. Oh yeah, it will be negative. So you're saying as you go along from x0 to x2, the pressure decreases. So this will be minus 1 kilopascal per meter. It drops. It doesn't increase. It drops. So that minus has to be included. So this will be minus 1.80 kilopascal per second. Good catch. So the total will be 15 kilopascal per second minus 1.80 kilopascal per second, which gives us 13.2 kilopascal per second. Make sense? So tell me what are you taking away from this entire discussion about total rate of change?
Time and position.
Depends on time and position. The total rate of change with time is not only about the change with time, it also dependent on what goes on spatially as you move from point to point. Okay. For those of you who are still writing, maybe take 10 seconds, finish writing, but I want you to listen to me for the next minute. So one way to remember this, which has worked for me, so I'm sharing it with you. If I localize a measurement device at a point and just record its reading, that reading is going to be what the local rate of change is. If I let a measurement device float along with the flow with the same velocity as the flow, let it go travel at the same velocity as the flow itself, wherever the flow goes, it will go at the same speed, at the same rate. That measurement instrument will record this. It's like if I drop a temperature sensor in the river and let it flow along the river and somehow it is still transmitting that data back to me, that transmission will encompass all the spatial change because the temperature sensor is traveling with the water, and whatever the water temperature goes up or down along the path, that will be reflected over here. Okay, so one way to close this discussion. Can I erase this? Have you written this down, these numbers? Okay. partial P over partial T can be obtained from the readings of a measurement device that is fixed at a point in space. Just bolt it there, it will keep reading whatever the value of pressure, temperature, or velocity at that point is. That's how you obtain the local rate from experimental data. The spatial rate of change, u times dp dx, can be obtained from the readings of a measurement device that is, until here everything is common. Until here everything is common. I'm going to write those spaces again, dot, dot, dot. The spatial rate of change u dp dx can be obtained from the readings of a measurement device that is following the flow at exactly the same speed or same velocity as the fluid. It's like an imaginary sensor that can ideally trace the flow, move along with it, and continue to transmit whatever it sees. That will be the spatial rate of change. Okay. Is it making sense? Is it helping? Yes, no? Okay, I'm going to test your understanding here. All right, I'm going to try testing it. Stop this. Okay, listening time. Tell me the answer to this. So here is here is Earth. Let's say we put a satellite, and in satellite we have an instrument to measure radiation, to detect radiation from the sun and from the entire cosmos. Okay, and the satellite is of course beaming the data back to the control station down in Earth, where that data gets plotted. Okay, so you have data that goes some kind of cyclical activity over time. So this is like radiation intensity measured by the sensor. Don't worry about the units. It's a quantity that it's recording and beaming back to the ground station. So this is one situation where you have a satellite that is making orbits around the Earth, and when it's facing the sun or away from the sun, it's going to have some cyclical activity. And then think of like a space probe that we launch, a space probe like Cassini or all the probes that were launched in the past, Voyager that went past Saturn, Jupiter, and so on. And the space probe is traveling at a certain speed, and that speed changes over time. Okay, and that space probe also has a radiation detector. When it goes near Jupiter, or when it goes near Saturn, or sees the sun, that probe is going to emit some signal, and that signal is also beamed back to Earth. And as the observer there, you are plotting that also. Okay. The quantity plotted by the satellite and the quantity plotted by the space probe, can you tell me what's the difference between the two?
By the satellite is your either velocity gradient or your pressure gradient, and your Voyager is going to be your velocity.
Okay, I'll come back to you. You wanted to say something?
So would the satellite be like the recording the spatial, and then the probe would be recording the local components?
Are you calling this, what are you calling this?
That's the satellite.
And this is the probe. So you said the satellite will be recording the spatial and the velocity, the probe will be recording the local. Right? Okay. I'll come back to that. Okay, and I want to talk about. Any other response? Anybody else wants to say something? If you think of the size of cosmos or size of space, a planet and its immediate vicinity is like almost a dot in that entire space. You can think of, even though this satellite is going around the planet and it has all these variations, if you zoom out over a large distance, it's almost mapping what goes on in a small volume. It's kind of localized to the planet, that's my point. This satellite is just recording what happens around this planet. It will tell you clues about the seasonal cycles, the solar activity, and the amount of radiation and so on. With me, this one is giving you information that is local to this sphere, local to this volume. Would you agree with me? The probe, on the other hand, is going through space. It's flying by different planets or even a star or whatever. It is looking at each entity on its path for one snapshot. It's seeing Saturn once or seeing Uranus once. It's not seeing everything all the time. This is seeing everything all the time, but that everything is focused on a small local volume, whereas this is seeing a lot of things for just 1 second as it passes by. So this will be the information recorded here is spatial, because along this you also have the velocity effect mixed in, whether it moves fast or slow, that also matters. That is, let's say you have Jupiter and a Saturn, and the satellite or the space probe just zooms between the two, it will look like the temperature is changing rapidly. But that's because the satellite is moving fast, not necessarily that the temperature is changing fast. Over here though, it's not necessarily moving in a big picture sense, but it does have these seasonal changes, which means something that is emitting light, like the sun, has some radiation changes, or there is day and night, or clues of what happens here is kind of embedded here. This analogy kind of helping it. So these features here, velocity effect is embedded into spatial rate of change, whereas this is local, only time rate of change is embedded here. Okay. Questions before we move on to the next topic? Can also be comments. Anything that you have seen in real life that you want to seek an explanation. Hey, I saw this. Is it related? Can we explain it? Maybe I should do participation exercise where you bring some problem from your life and ask the class for how to understand this. Because what either you are very curious and you are not telling me because you don't like me, or you're just not curious enough to bring something to the discussion. Can we think of something from everyday life? Yes.
It's not either of those. I just don't really understand what we're doing.
Okay. What I'm trying to ask is whenever you see a accelerating fluid, I want you to tell whether that acceleration is driven by local factors or by spatial factors.
So like a river would be like spatial.
River would be spatial. We use that analogy in our discussion. Can we think of other examples where a fluid is accelerating and we are asking ourselves, is that acceleration driven by local or spatial factors?
So if I open a faucet, for instance, that
Okay.
would be a spatial because I'm providing new area, or is it local?
Good question. So he's talking about opening a faucet and water is flowing out. Let's think that water is flowing out nice and like in layers. We call it laminar. And if you just look at it, the water is very steady. You just open the tap, the municipality sends the water at a certain pressure, and when you open the tap, it flows out nicely. Now you tell us, the rest of you, he has raised the question, you tell us whether this is a local phenomenon or something driven by pressure gradient or the fact that pressure changes along the length of the pipe.
Did not be both at the same time.
It can be both at the same time, but in this case, when you open the faucet, what actually causes the flow to happen? Let's think about that.
Uh, removing like something blocking the pipe.
Right, so you have a tap and you have like a valve or
A
a
valve,
faucet, and then you have something that drops the water. So you remove this barrier. What does the municipality actually do? Why are we paying them water money, water bills?
Sending water to your house.
How do you send water? They pump, they have a massive pump. Every city or every maybe region has one. They pressurize the water and they store it in their tank. And they have feeders or basically pipe that goes to each neighborhood and then to each house. The water that you open is highly pressurized. That pressure is being stopped by your tap or your faucet. And the moment you open it, that pressure is causing the water to flow. So it sounds like the pressure is initially, I'll call this P1 and I'll call this atmospheric pressure PA. It seems to me P1 is much greater than PA, right? If P1 were less than PA, then you would have suction. If P1 equal to PA, you would not have any flow. So off the bat, P1 must be greater than PA for our taps to work the way they do. Okay, and there is, of course, your municipality or your corporation, whatever water is at a central location where they highly pressurize it, and then they have piping that run to your house. Okay, when it enters your house, it has a certain pressure, and then you open the tap, it flows. It sounds like the fact that there is a pressure difference between this location and this location. I'll call this x1 and x2. x2 minus x1 divided by p1 minus pa seems to be driving the flow to me. Would you agree?
Yeah.
Right? This pressure gradient drives the flow. If drives the flow. If it were not for this pressure gradient, you won't have flow in your taps. Right? So the acceleration that you see here, the acceleration of water here is due to u times du dx or spatial factor. Thank you, Isaac. You brought an example that helped us make a practical one. Can we think? Yeah.
So if we do that, like, we're mapping out the total, that's gonna give us the change in pressure,
Right.
not the acceleration. So how do we describe the acceleration?
Okay. So again, good question. So let's say you have your tap. I'll just take this example, okay? And I'm going to stick my imaginary velocity probe. There are different technologies to measure liquid velocity, but I'm going to take this hypothetical probe, which will allow me to sit there, and record the velocity over time. Okay, so I'm going to record at this point, I'll call it P, the velocity at P over time. Okay, initially there was no water. And then you open the tap at time 0, open the tap. What happens? The water gushes out. The velocity has to rise from 0 and it will stabilize at some value. And after that, it just goes to become constant at that point. That's how taps work, right? Once you open them, they look steady. But from the moment you open to the moment they become steady, there is a certain rise time. Right? So question to you is, what is the local acceleration in this segment before they became steady? And what is the local acceleration after they became steady?
The acceleration after it becomes steady is 0.
The local acceleration over here is 0 once they are steady. Over here, it is non-zero. Okay, so you sit there with your velocity probe and it shows you there is some activity initially and then it goes to 0. Then you don't get any useful information from the velocity probe because it's just going to read the same thing forever until you run the tap. Okay, then let's say you put another velocity probe a little bit downstream. We'll call it Q. This is the jet of water that's coming out. As it comes out, that jet will want to slightly expand. When it slightly expands, its velocity will slightly drop. So whatever VQ is, it will be slightly lower than VP. It will slow down or as it expands. That's how rivers go, right? They come out as a jet, and then as the cross section widens, they slow down. Okay, so VQ is less than VP. You're with me there, right? And there is a finite distance between P and Q. We'll call it XQP or XQ minus XP. Okay, there is a finite distance. We'll call it XQ minus XP. Yes, good. So then this velocity VQ minus VP divided by XQ minus XP. This is the velocity gradient. Velocity gradient.
So that would be your local thing.
This is velocity gradient. I'm not talking about local or spatial. Just saying, if I travel from P to Q, this is how much the velocity is changed. Okay. Now, if I want the total acceleration at Q, I would write this is the local acceleration at Q plus the spatial acceleration at Q. Right? Whether you look in the first few seconds or later time, local acceleration will either be 0 or non-zero. That's what we established from the first discussion, right? So then, local is easy to understand. Just fix on a point, just look at the velocity over time. At that point alone, don't look at the neighborhood, you get it. This quantity here, this is like the velocity at Q, right, at VQ, multiplied by the velocity gradient at Q. This is the acceleration of the fluid. Even though your fluid looks very static and it looks very steady, it is accelerating, and this is the acceleration. Okay. The connecting, that equation is very easy to compute, but you have to really pick up some real world scenarios to understand. Okay. Any other situation? Yes.
So since the water, when it comes out of the faucet, is in free fall, how does gravity come into play since gravity is so rich in water?
Very good question. So he's asking, where does gravity factor in here? Now we learned in chapter 3, Bernoulli's equation, P plus half rho V squared plus rho GZ equal to a constant. If it's at least steady laminar flow, which can be reasonably considered inviscid or without viscous effects, you can think of applying Bernoulli equation between P and Q. So this relation, if you apply it between P and Q, it will give you a relationship between how pressure changes and how velocity changes between those 2 points. It gives you one more equation that also brings in the height, the gravitational driving force. Okay, if you look at the units, a pressure difference like a pump, a velocity difference like a pump or gravity produce the same effect. If your goal is to supply water, you can have a massive pump in the middle of the town and push the water to different neighborhoods, or you can have a massive overhead tank, store the water above, and use gravitational potential energy to drive the flow down to the homes that are in the ground level. That is why before pumps were invented, every town would have a massive overhead water storage to drive the water. It's free, just have to somehow store it there, maybe catch rainwater and then let it out. Or use horses or paddle wheels or something to get the water up and then let it out so that you can supply it. So a pump and gravity, at least in terms of the math, they are completely interchangeable. What you accomplish with the pump, you can accomplish with gravity, but when it comes to implementation, there will be a lot of details. Okay. Any other example? Yeah.
So the two formulas, they're both using velocity, but they're describing different things. So like you wouldn't have to, the acceleration is caused by the change in
Pump
pressure.
or a height change.
But you don't have to have the pressure to find the acceleration because you can just use the velocity.
For only velocity, yes. Only velocity, you don't need pressure, that's correct. But velocity change is almost always caused by a pressure change. They are related through this Bernoulli equation or more complicated equations that do momentum balance. Okay, I think you have raised a valuable insight here. What you are saying is, I'll write it here, maybe something you should write down. Acceleration, or I'll write it the other way. A change in velocity due to either position and or time causes acceleration. That's what you're saying, right? Change in velocity either through one or both the reasons causes acceleration. But what causes change in velocity? Change in pressure causes change in velocity. And that change in pressure can come about due to a pump, due to gravity, due to your heart pumping. Heart is nothing but a biological pump. It can be due to your kidney, which uses osmotic pressure pressure difference can be created by anything. It can be a suction tube, it can be a pump, it can be anything. But in the end, a change in velocity is always caused by a change in pressure. How you cause the change in pressure can vary. I'll write that down. How that is caused may vary. But at the core of it lies a change in pressure, somehow.
So I think what he was asking was the reason you wouldn't do gravity in the gradient equation is because it's like, you can describe acceleration using F equals ma, but you can also do it just as the rate of change of velocity. It's two different things to describe. You can get the same information from it, but they're describing different interactions.
Right, right. Physically, they are different interactions, but mathematically, it's the same quantity, same unit. That's correct. And not within this course, maybe in the future, you will also learn pressure itself is not only due to fluids. Pressure can be caused by ions or electrons or radiation. Have you heard of what are called light sails? What is the sail? Being fluid mechanics people, we should say what is a sail, right? It's a mast with a cloth or a large area which responds to the wind blowing and uses the energy in the wind to push the boat along. Very old concept, right? So that cloth or the sail uses the fluid pressure and converts the motion of the air into propulsion. Okay, there you think the fluid exerts pressure. If you try to make a satellite or a space probe, you don't want to do propulsion all the time. To save on fuel, what they do is they know the sun is radiating light, and light consists of photons which carry some teeny tiny bit of momentum. They have these large plates which are like very light sheets, and when light falls on them, due to the momentum that those photons bring, by billions and billions of impacts, they slowly start exerting a net force and push the spacecraft forward. So the idea of pressure itself is universal. It's not restricted only to fluid flow. It's much broader than that. Okay, and I'll leave it at that. All right, good. I wanted to do all of this in the first 10 minutes, and we are at 12:25 now. Hope it was worth it. Can I erase this? Do you need time to write? We good? So the next topic is called Reynolds transport theorem. Okay, it is covered in section 4.4, and after a very lengthy derivation, they get you this equation, which right now doesn't make sense, but I'm going to try and clarify. I want to start with an example. Okay, you have a volume. Listen up. You don't have to write anything. So if you have a volume, let's say something like a inflatable swimming pool that you can inflate with air and then keep it up and then you can play with. How you initially get something that comes in a package, you remove it, you connect it to a compressor or a air pump, or if you really want to you're really strong, you might want to blow your own air. Hope you don't pass out. No. So you inject air. Okay, the shape inflates. The shape inflates. And if you had a pressure gauge connected to this, the pressure gauge reading would start to climb up. Right? So this is the pressure as a function of time. Pressure in this whole volume or balloon or tire or inflatable toy that you are trying to inflate. Okay. As you pump air in, air accumulates inside. All right. So what is the rate at which the mass of the air in this volume will grow? If I ask you that question, what would you say? It has only one inlet. This pressure gauge is sealed, no leakage here. So what is the rate at which the mass of this the air here will grow?
If the air enters the system.
At the rate at which air enters the system. So this rate at which the mass will change should be equal to the rate at which air enters the system. With me? There should be nothing to write here. It's all semi-qualitative discussion. I'll give you time. Okay. Now suppose there is a leak over here. A very tiny leak that you can't really say, but you do this instead of your pressure climbing up and reaching some steady value. Okay. Your pressure continues to climb, but it climbs at a much lower rate. And you just see the data. You can't really tell from the data whether there is a leak, but you do this for a much longer time. Let's say the product specification says it should be inflatable in 10 minutes of pumping. But you have been doing this for 40 minutes and you still haven't reached that target pressure where you can call it off. So there is a teeny tiny leak. Okay. So in that case, if I ask you, what is the rate at which the mass of the air in this volume changes over time, what will be your answer?
You do m dot air in minus the leak.
M dot air in minus M dot air through the leak.
The thermodynamic.
Thank you. He's basically saying this is just a balance. I already know this. You do. It's about just what comes in minus what goes out. You did this with your enthalpy balances for your, thermodynamic one, right? So if I ask you, what is the rate at which stuff accumulates in the balloon or the toy? It's the sum of the flow rates at which it comes in minus the sum of the flow rate at which it leaves. Can you generalize this a little bit if I say there is more than one entrance for the air to come and there is more than one leak for the air to leave? Can you generalize this?
Sigma m dot n.
Yeah, just summation.
Louder, please.
Summations of both
Summation of all the inlets.
minus.
Summation of all the inlets of m dot minus summation of all the outlets of m dot. If the two were exactly balanced, what would you get? You would get a net accumulation of 0. If the two were exactly balanced, you would get a net accumulation rate of 0 if they are balanced. Right? Rate at which m dot of the system either increases over time or decreases over time is simply equal to inlets m dot minus outlets m dot. Thermodynamics formula. In fluid mechanics, we are not only interested in the global balance that stuff comes in, stuff goes out. We also want to know, you have a tube here, right? per tube here. Now, what is m dot? What is mass flow rate? How do we think about it? When you inject fluid into this chamber, you're not only worried about the overall flow rate, you are interested in what velocity profile with which that flow comes and across the cross section. We want to pay attention to the flow velocity itself and not just to the mass flow rate. Yeah. So we want to be able to say how to express m dot in terms of fluid velocity V and cross section area of the tube A. That is the key question for fluid mechanics analysis. Do we know? Do you know how to express m dot? How to express m dot in terms of the velocity of the fluid across the cross section and the cross section area itself. Do we know that?
What if you need the density as well?
Of course, it also has to have density. In terms of the fluid velocity and cross section plus density. Do we know? Even not for most general, but at least very specific, do we know a relation between density, velocity, area, and mass flow rate? Rho V A
For
equal to m dot. That's correct.
incompressible, right? This is only for incompressible.
This is true even for compressible, but before that, I want to address under what conditions it's simply V times A. By saying mass flow rate equal to rho VA, what are you implicitly assuming, but maybe you are not aware or not fully aware? When you say rho VA, what are you assuming? What goes with this statement?
It's just constant.
No, that doesn't, actually, that's not a part of this answer. I'm just talking only about V and.
Velocity in X of V, velocity in A are constant.
So you have a pipe, let's say, and it has a certain cross section, radius r, and you would say the area is pi r squared. Right? It may not, it may be a different shape, like it could be a square cross section, triangle, doesn't matter. It has some area, right? And then you have velocity, we'll call it V. When you take V and A, what does that represent? What is V and A?
Volume flow rate.
How? Can you explain the word volume flow rate to me without using the word volume or rate?
You have a mass traveling along an axis that is going through some pipe with an area along two different axes. So
Yes, from your statement, I'm going to leave out pipe, I'm going to leave out axis, because what the concept of VA or flow rate is much more general than a pipe. Even if it's not a pipe, if it's some other structure, you can still think of flow rate. So let's leave out the pipe thing. If you take this quantity, okay, and it is flowing across a region A, literally what is velocity? You tell me velocity is rate of change of position of the fluid molecules. So if a fluid layer started here at T1, at T2 it's over here, and this rate of change is what you call velocity. It's like literally saying in this unit of time, that is in delta T equals T2 minus T1 seconds, the fluid travel delta x units of distance, which leads to a velocity leading to a velocity v, that is delta x over delta t or dx over dt. Don't worry about the dx over dt for now. Just focus on this delta x over delta t. This is delta x. Yes. Okay, so it swept a certain distance. And in that certain distance, if you take this area and multiply by the distance, the volume of the cylinder that it swept, is delta x times area, where A is the cross section area. Yeah, and this volume was swept in delta t interval of time. So it's like a little pillbox that just moves through, and the rate at which it moves through would be delta x times A divided by delta t, or this is V times A. This is where the VA comes from. Maybe you already knew this, maybe this is new, but it starts here. VA comes from the volume flow rate, Q is equal to VA. The implicit assumption while writing that is V is constant across A. The math will look the idea of a pillbox will only work if velocity is the same across the entire cross section. Right? So this assumes V is uniform or constant across A. What if it is not constant? What if the velocity is not constant? Okay, so now it's going to get realistic.
Bro, a integral v, I mean a function of v dt.
I'll pose the problem, then please tell that again. So you have a pipe. Instead of having a constant velocity, the velocity is 0 at the wall, and then it increases and then goes back to 0 at the wall again. Let's say we have a velocity which changes with the radial position. If you are at a radius of 0, it is maximum. If you are at a radius of r, the velocity is 0. And for what we'll see later in the course, this will be a parabolic profile. Okay, it looks like a parabola. The velocity is a function of r. Now, what that literally means is the velocity at the center line is faster than the velocity on either side of the center line. Okay, so if I take this v of r and I just multiply by a, would that give me flow rate? Yes, I see two people nodding. No, it won't give me flow rate. The reason being, this is not the same velocity everywhere. It's different at each point, right? So when I want to use this equation, I need to pick an area that is small enough such that over that little area, I can think this is constant or this is uniform. So pick, this is not Q. This is not Q. So what I'm going to do, is if I have a cross section and I have a velocity profile, I'm going to pick a small area, that is, let's say this point is at a distance r from the center line, and this width is dr. dr is a small radial segment. Meaning if I draw the side view, it will look like this. Here is r, and then I have dr, okay? Listen up. Across this cross section, across this tiny cross section, I think my velocity is constant, or I assume my velocity is constant. So if I ask you the question, what's the flow rate across this tiny part of the cross section, not the entire, just this tiny part, it would be V of r multiplied by the area of this cross section, which I'll call dA. Now it is flow rate. Even though it's small, it's a tiny segment, it is now flow rate of velocity times area. Okay? And a little bit of math. What is dA? So if this outer circle is pi r plus dr, and the inner circle is pi r, sorry, the inner circle radius is r, and the outer circle radius is r plus dr, dA would be the outer circle area minus the inner circle area, which is 2 pi r dr plus dr squared. And I since started with the assumption that this is a tiny section. We always throw out the second term and call this as dA. That is, dA depends on dr, so we are going to do integration soon. 2 more minutes. So the flow rate is V of r dA. Okay. This is only for a tiny segment, but I have to think about the entire cross section, for which the radius varies from r equal to 0 to r equals, let's say, uppercase R. So this is from r equal to 0 to r. So this is 0 to r, V of r, 2 pi r dr. We don't want to do math today, okay? But what I will say is, you started by saying Q is equal to VA. That is only true if the velocity is just a constant. If the velocity is not just a constant, Q would be integral of V dA. And how to use vector notation to express it so that it can be applied for any geometry, any orientation. We'll see those details in the next one after spring break. Okay. We are going away for a long time, like nearly 10 days. Some of this could be forgotten. It would really be helpful if you maybe revise or rewatch the lecture, at least parts of it, to make sure you are caught up before you come to it. Okay? Thank you.